Well, this is part 2 of the eigen video. Now, in the last video, we did step 1, which is define this finite element structural model, and we confirmed that the mesh looked okay. We did some basic checks on the rigid body mass and the mesh and so forth. So now we're going to go to step 2, which is actually solve the eigenvalue problem, and all in part of the basis or the process of finding the reduced basis. And that's fairly short in terms of the sense that it takes a little bit longer to run than just inputting the mesh, but there aren't too many steps other than running it. So we're going to combine that step with this step here. In terms of this video, we're combining them in this video, which is viewing the mode shapes, which is an important step. We're not going to do all the viewing that you would want to do in a real problem, or in a problem you haven't solved before. I've solved this problem several times. So, but we'll put all of that in one video. All right, so let's look at the input file again. We saw that defining the mesh itself was pretty quick. So, I'm not going to save those results and then read them in. We're going to go through that process subsequently. Certainly the eigenvalue problem, once you've got that, all the bugs worked out of that, that's not something you're probably going to want to go through every time as you try to do different things with this in this analysis. So we will do it there, but here we're just going to start from scratch, if you will, and run through the mesh generation as well as the eigenvalue solution. So I'm going to comment out this return here, and therefore it'll go through what we did with the previous video and then all the way down to the end here. And so let's look at what we're doing here. So P2 sparse. So Form K and Form N form what's called the stiffness and mass matrices and profile storage. It's fairly efficient, but it's not as efficient as sparse storage. And so we're going to convert P to sparse, profile to sparse. We're going to convert those matrices to sparse storage format so that the eigenvalue solution goes faster and we require less memory. So K.kstr is where Form K puts the stiffness matrix. This is a location of the diagonals of the stiffness matrix in that storage, and it's a accounting thing that's needed. And .mstr is the profile form of the mass matrix, which is formed by Form M. And this is going to convert those profile storage matrices into sparse matrices. All right, so eigenval is the solution, or is the command that finds the eigenvalues. So we need to tell it how many frequencies we want to find, and we defined pound frequency, pound freq before. We defined the maximum number of iterations we wanted and the number of digit accuracy we wanted. We defined the shift. And here, okay, so I said I would come back to rigid here. So what this says is so the way the eigenvalue solution works is it sets up an estimate for the mode shapes and then starts refining those and iterating on those to get them to be the actual mode shapes. And so what this says is, okay, I expect a certain number, in this case 6 rigid body modes. So form initially the 6 rigid body modes associated with surge, sway, heave, roll, pitch, yaw. And it says, okay, define those about this CG here. Frequency, sparse tells it to use the sparse. Random is just the way it generates the initial guesses for the eigenvectors. And frequency says find the frequencies. In other words, the eigenvalues are the square of the frequencies, so we want the frequencies. So .omega is going to have the natural frequencies in radians, so that's just taking the square root of the eigenvalues. And so this says print the natural frequencies so we can see them. And then I'm going to convert the natural frequencies in radians to periods. So natural periods are probably easier to interpret than natural frequencies. Certainly natural frequencies, radians per second, is pretty hard to interpret. And so one either probably wants to convert to cycles per second or hertz or a period. So we're going to convert to periods. Well, so the period is equal to 2 pi over omega. So we're going to do a little bit of calculation here. So first I define pi. The command pi, lowercase, defines pi. In this case, I'm using the variable name capital Pi. And then I add them together to get 2 pi. And then I'm going to copy the frequencies to an array called, or a vector called nat periods, natural periods. And then I'm going to take the inverse of the frequencies, and then I'm going to scale that matrix or vector by 2 pi. So now the result is nat periods is going to be equal to 2 pi over omega. And so then I print those here for viewing. Sparse matrix clean, that's a command that just deletes all the arrays associated with sparse storage. It reduces the storage in the database, which we want to do because we're going to save it for future use, and so there's no point in schlepping those things around. I'm also going to remove .kstr, .mstr, because they're large matrices as well. Actually, they're stored in vector form, but they're large as well, and so I'm going to get rid of a bunch of stuff I don't need anymore to reduce the size of the database. And then I issue the command save to save the database so we can read it in again later without having to go through this whole calculation again. Okay, let's run this problem. So I'm going to start Hydran. Now, if I open the project up as eigen, it's going to overwrite the output file that was created from the previous run with the same name. So if you want to save an output file from a previous run, you either need to use a different project name or you can rename the .out file. So I don't care about the old the output file from the previous video because we're going to go through the same thing as we did yesterday in terms of generating the mesh, so nothing's lost. So I'm just going to click OK here, and I'm going to put the window there. Before we get started, I want to come back to help on the commands. As I mentioned in the previous video, we can get it either from the PDF command reference file, we can get it from the help.out file, which is available online from the website, or we can, if we're working interactively and we just want the command, the help on a specific command, I can type in help file in, for example, and get exactly the same information as in either the help.out file or the command reference file, because this is how that information gets into help.out or command reference. All right, so let's do file in, and it first goes through and forms the mesh, and now it's solving the eigenvalue problem. I may skip a little bit here depending on how long this takes. We see it's going through some iterations. I don't believe it takes very long, so there, it's done. So we can view the results here, or we can view it in the .out file. So we can see here it took us 14 iterations to find the 30 eigenvectors and eigenvalues. And it gives some timing solutions here. These are the frequencies in radians per second. Now the first 6 should be 0. Well, numerically they're not. It's unlikely that they're going to be 0. They may be, but unlikely. But you can see that these are very, very small, especially the 3 translations. These are also quite small compared to the first flexible mode, which is 2.78. The largest one here is 0.045. So you can see that there's several orders of magnitude difference. So we're pretty confident that that's correct. The 2.78, that seems reasonable. It does take some experience with that. And it goes all the way up to 43.5, but these is radians per second, so not as easy to interpret as, say, natural periods or cyclic frequency. So we see now, this is 2 pi over omega, so ultimately, or actually these should be infinity, right? But they're just very large numbers. So the smallest number is 138 seconds. But officially they should be 0. Okay, so then the first natural period is 2.25. The smallest period is 0.14 seconds. We know that there's very little wave energy below around 5 seconds. So these these periods are well below where the significant wave energy is. And so that's a good thing because that means we're not going to get resonance. That doesn't mean to say that the larger wave periods don't excite these smaller natural periods of the structure. They will, but we won't be having resonance. At this point, we would need to consider how many of these frequencies are we going to use for our hydroelastic analysis. And one way of doing that is to look at the frequencies, but we also need to look at the periods, and we also need to look at the mode shapes, which we're going to look at in a minute here. But we need to inspect those for errors, potential errors, funny things going on that are non-physical that we don't want showing up. That's the end of this input file. And so I said we were going to do 2 processes here. Let me come back to this guy. So we just did step 2 here, found the eigenfrequencies and normal modes. The next problem is to view the mode shapes. And so we're going to, because this went so quickly, we're going to do this here as well. So I need to come here. We see that the next input value is eigenview, which view the eigenvalues. So, eigenvectors. Now this is meant to be run as a separate project. We first need to read in the database from the eigenvalue analysis. We don't want to rerun that. So we've already run that. We've saved it. We saved the database here. So we're going to read that in so that we don't have to run the eigenvalue analysis every time. So you can see that the .db file, .database file is written here into this folder, and we can just read it and start up from where we left off. Now there are several ways of starting a new project. We can quit Hydran XR and start it up again and type in a new project name. We can come up here and select Change Project. Or we can just type in, for example, New Project here and do it that way. Well, let's do it. We'll do it this way. We'll change the project. And so that opens up this window. We want it to be in the same folder. So I'm just going to say eigen_view. All right, so now we see that we have a new project name and new output file and a log file. All right, so let's come back and look at what we're doing here. So we're going to read the database. We're going to copy. So the eigenvalue command puts the eigenvectors in a .phi matrix. We're going to make a copy of those. So we're going to copy those to .disp. And then we kind of need to do that because the export graphics command expects the displacements in the array .disp. So export graphics with these options are going to give us what we want. -gmesh tells us that we're going to get a .msh file format. We want the deformed shape, and case equals 1 through 19. So this is going to be mode 1, mode 2, mode 3, and so forth. Autoscale says to scale the displacements to convenient size for viewing. File tells it what file name to use for the different modes. So we write from mode 1 down to mode 19 here. Now, Hydron GUI will only view one mode at a time, so we have to write them in separate files. We can also export all the modes into one file, and this could be used to view in a separate graphics program, for example, like Gmesh or TechPlot. And in that case, that's what this does. It writes all the modes to a single file, and then it's much easier to cycle through the modes in those programs than it is to view each mode individually in Hydron GUI. And finally, sometimes it's convenient to animate the mode shape. It helps with the visualization substantially. And so we can use the option in Export Graphics to do that. And here, for example, we are exporting mode 5. We're using 20 steps. We're subdividing the frequency by 20 steps, so we get 20 frames over one cycle. And then, of course, this is the file name that it's written to. And then you can use that to animate the modes, view animated modes in a program like Gmesh or TechPlot. All right, well, let's run this project. So we'll just type in file N. And it's done. And so we're only going to look at the modes in Hydron XR GUI right now. I'm not going to open up, for example, Gmesh and look at the modes there. So we're going to go to here, and if we look at, mode 1's not going to be very interesting. It's just surge. Same with mode 2 and 3, surge, sway, heave. Even the rigid body rotational modes. Important to look at them to make sure they're correct, but we're going to start off with looking at mode 7, which is the first deformational mode. So again, using the mouse, I can zoom in, rotate, drag. So this looks like what we kind of expected, right? Pretty typical for this class of structure would be a vertical bending mode, and that's what we have here. We can see there's nothing fishy going on. It's all what we would expect. And then if we go to look at mode 8, let's see, mode 8, that would be the second deformational mode. And again, a little tedious in a way, but we see that it's the second vertical bending mode. And again, it looks pretty clean. Nothing, no spurious, unanticipated local modes that shouldn't be there at this natural period or natural frequency. And we can look at mode 3, deformational mode 3. That would be mode 9. So there. So let me zoom in here, and we see now that this is the horizontal bending mode. Again, what we would expect this mode to show up at some point in time as well for this class of structure. We can see this just involves bending in the horizontal plane. So we would, this is all good. These are good results. So let's go look at the last mode. Well, let's look at mode 18. So we're going to go down and look at mode 18. And this is now kind of what we really don't think is probably a realistic mode. Most likely involves a lot of local deformation here. It depends on how you've stiffened the shell, the plates. So remember, we didn't include the shell stiffeners explicitly. In fact, we didn't design those. I mean, that was one of the reasons we avoided having to do a detailed design like that by just including a smeared bending stiffness. But these are the kinds of deformational modes that the stiffeners are probably going to prevent from happening, these boils, so to speak. This mode shape and the natural frequency associated with it is so high that it's unlikely to contribute much of anything to the structural response. So we're not too worried about it. You can see that it's the top plate that's having these kinds of behavior predominantly, and that's because we put so much of the mass on that top plate, if you'll recall. So probably not what you would see in a practical structure, but these are the kinds of modes that you want to avoid. We would have seen these a lot sooner if we hadn't used a bending stiffness or appropriate stiffeners. They would have shown up straight away and would have resulted in poor results. Here they're not going to affect anything because the natural frequency is too high. And that is really the end of this video, and we're going to pick up with the next step in the workflow with the next video.